Okay, it's a pleasure to have Alexander Radovic from Fermilab. He did his PhD in the University of College London with J.D. Thomas, where he was a key researcher in the updated measurements of the delta M atmospheric theta 2-3, which were later used to have what used to be, I guess, the most accurate measurement of theta 2-3 by Minos. Later on, he was hired by the College of William and Mary and was stationed permanently at Fermilab, where he is the convener of NOVA for the muon neuron disappearance, and also a nominal member at DUNE at the same time. And today he's going to tell us about his work on neural networks.
Thank you. Yes, so I'm going to try and talk you through how deep learning has been used to revolutionize event classification at NOVA, and to give you some context for why NOVA is a pretty natural fit to actually use this for physical measurement and propagation. So just to introduce you to the field of neutrino physics if you don't pay too much attention. Of course, we had a somewhat infamous beginning with the theorists that suggested the neutrino apologizing for suggesting a particle that could not be detected. Of course, that's patently false these days. And even in challenging environments like the NOVA far detector, where there's an awful lot of cosmic noise, we can do a pretty great job of isolating neutrino interactions. And the game becomes more of precisely identifying them once we've actually found them. So what is NOVA all about? So we have a few primary physics goals. One of them is continuing to push on the atmospheric mixing parameters. Clearly this is something which has been a large part of my career so far. And so we want to continue to make precise measurements there, but we also hope to make, we want to do that taking advantage of a neutrino beam and looking for depletion inside of it. So the gain in neutrino oscillations is, of course, that your beam is not the same one at beam end as the one that you started with. And here, the set of oscillations that gives us a window into the atmospheric mixing parameters is the depletion of muon neutrinos. There's a simple cartoon version of the equation here. This is not what we actually use or what's really going on, but it gives you an idea of the leading order terms. And you can see that you'd expect the magnitude of this effect to be related to the mixing angle of theta 2-3, and you expect the Radovic dependence to be related to the mass volume. It means that when you observe your real spectra with oscillations, you'll see a dip where oscillations have kicked in with some Radovic dependence, and the magnitude will very neatly give you that theta 2-3, and the shape will allow you to constrain delta and square through. At least first order, that's the game characterizing and measuring that here. But we don't want to just talk about atmospheric mixing parameters. We want to say something about some of the more interesting, exciting parameters in neutrino oscillations, particularly delta CP and mass hierarchy, the things which give us a potential window into leptogenesis and all that good stuff. To do that, we need a different sample. Instead of looking for disappearance now, we're looking for the partner oscillation of muon neutrinos into electron neutrinos. The oscillation formula is actually even more complicated, even looking at a very simple expansion, again in this case, but you can get an idea of what's going on. You can see theta 2-3 pops up again. This gives us some window into actually the optimal theta 2-3, which is interesting, but most importantly it means that this measurement and the previous one are going to be coupled to each other. In order to say something about the rest of this formula, you want to be able to pin down this angle as well as you possibly can, so we end up doing joint fits. Theta 1-3 comes from the reactor experiments these days, so you don't have to really worry about it. It's measured very well. Delta squared 3-2 again from our other partner measurement. It's important. But the exciting things, you see there's a delta CP component, so we have the potential to say something about whether there's CP violation in the neutrino sector. And we also get a window to the mass hierarchy, because it turns out that electron neutrinos understandably experience an extra interactions in pass-through matter. We have a lot of electrons in the Earth, we don't have many muons or taus. That actually modifies their oscillation probabilities and gives us an interesting window into the mass hierarchy. It means you end up with oscillation probabilities which are perturbed depending on whether you assume the normal or the inverted hierarchy. Again, we get this effect because our baseline is going to go through that. What baseline am I talking about? So the whole game with NOVA is we're going to try and study neutrino oscillations in the way that I just mentioned over our 810 kilometer baseline with two functionally identical detectors, the world's most powerful neutrino beam. That beam uses main injected protons to generate a lovely beam of parameter muon neutrinos. We'll see it again here in the detector, and then again we actually sit slightly off the main axis of the beam. That means we access a tightly peaked subset of the piles of kernels that give us our neutrinos. So we end up with a very tightly peaked beam set with our choice of baseline to give us an LMRE, or give a maximum for electron neutrino appearance. This is all about trying to make sure that the most exciting channel we have, the electron neutrino appearance one, is exaggerated as possible. It also kills the tail, which means you have fewer neutral current background events. I'll come back to that later. What are our functionally identical detectors? So they're a pair of sampling calorimeters optimized for electron identification, finely cemented, made out of low Z material, so that you'll be able to resolve as much as possible of the electromagnetic showers, which you'll see are important for one of our main signal channels. And it's reasonably active at 65%. The near detector is much smaller because the beam is more intense there, just geometry 30 tons of quantum from the source. Our far detector, 810 kilometers later, instead is 14 kilotons. I mentioned it was a sampling calorimeter. What is it actually constructed out of? Long PVC extrusions filled with liquid scintillator. Light is pulled out of the liquid scintillator by wavelength shifting fibers to avalanche photodiodes, such that you'd expect to see some 25 photoelectrons from a muon crossing the far end of one of these cells at the far detector. The planes are layered orthogonally, so you have a pseudo 3D reconstruction, which helps you to disentangle complex topologies like these. So at the top, we have the signal for that disappearance channel that I mentioned at the very beginning, muon-neutrino charge current interaction. Here, the really key signature is the nice long muon track and some associated ergodic activity. For the electron-neutrino case, instead of looking for a muon track, we're looking for an electromagnetic shower. This is where the choice of detector technology becomes key, because you have a better chance of actually being able to definitively show that it was an electromagnetic shower. And then we have a class of background events which come from neutral current interactions, where no lepton charge was exchanged. There's no information about oscillations, but they can fake out one of our signal samples with either a charged pion or maybe photons from a pi naught that look like an electromagnetic shower. So disentangling these from this kind of background and doing it for even the cases where they're not as beautiful as these cherry-picked examples is very important. One key advantage we have compared to a lot of other particle physics experiments is that we don't really have to worry so much about pileup. We have really exceptional timing resolution, at least for the sort of intensities that we look at, which mean that we can pretty cleanly pull apart different neutrino interactions, even if you do something really dumb, like just separate naively by time instead of using any space information. You see different interactions here at our near detector with somewhat higher neutrino intensity fall out very naturally from one another, which means you can consider them independently to first, second, or third order. This is a cute characteristic, which is that if you just look at the timing of all hits in our near detector, you can begin to resolve the shape of the proton pipe structure with the Lewis fields, which is kind of cute to do with neutrinos. So we don't leap straight to deep learning based techniques for identification. We already have some pretty well developed conventional PIDs. The simplest of these is the one we previously used for muon-neutrino identification. It's just a simple KNN using reconstructed tracks and qualities of those tracks which correlate well with muon. That does a pretty great job of separating neutral currents and muon-neutrinos, at least at slightly higher energies, because a long straight muon track is a very hard thing to miss, and it's kind of detected. We had to go a little bit more complicated with our more conventional PIDs for our electron-neutrino case. The signal is rarer, and the background is more challenging here. So we had a neural network, a simple fully connected neural network that took its input information like DDX or likelihood calculations and some other topological information to try and do projection. We had a slightly fancier library event matching solution that competed with this that was trying to just compare events to a vast library of simulated events. It's a little bit like scaling up a KNN to some extreme situation where you now take all information in the event to look up within a library instead of just looking at your nearest neighbors in some particular kinematic space. These did pretty much as well as each other. You'll see later they don't do as well as more sophisticated But before I get to what we specifically did with deep learning, it's probably useful to let you know what deep learning is. I know you've had a few seminars on this recently, but it's always good to cover these things again. And when I say deep learning, what I'm actually going to be talking about today, I'm going to be focusing on deep neural networks and convolutional neural networks. Again, I think you've seen some of these other exciting things in the last couple of months, and I'd be happy to talk about them offline. So just in case one of you has forgotten what a neural network is, it's a series of fully connected nodes. So each node in the neural network takes as weighted sum all the previous nodes in the network, pushes them through some kind of activation function. Historically, it was the sigmoid activation function. And in this way, many stacked layers can be trained to solve particular problems. That ability to train them is key, and how would you go about doing that? Well, you start by characterizing a problem, a loss function in the normal terminology, which characterizes the performance of the network. So for some kind of supervised learning, you come up with something like this, where you're comparing the labels you generate through the network to what you actually know the ground truth of the label should be. And the game is then trying to navigate training a network so that it progresses from a place where it doesn't do very well, where the loss function is very high, down to somewhere where the weights are set such that the loss function is giving you a really good result. You're going to have to do some work to make sure you don't overfit. It's all right to have a minimum, but you want it to be a good minimum, representative of a general set rather than just over your training set. You want the smooth black line case, not the jagged green one, so you want to add in some kind of regularization term to avoid overfitting. And the key that makes all of this work, the reason why neural networks are trainable at all, is that it turns out that as long as you're smart and you set up your loss function so it's differentiable, you can actually take a loss calculated at the very end performance of the network and propagate it all the way through the network using the chain rule to get a sense of performance of a particular weight somewhere in the network. That means you can then update weights using gradient descent, proportional to how much they contributed to either a right or a wrong answer at any given point. So that's the secret of why neural networks work. The actual structure itself and the fact that that can give you an answer is not so important. It's the fact that it's actually trainable that is most important. And it's pretty easy to see that straight away that a sufficiently deep neural network is going to be a really great function approximator and be able to do some pretty great things. Here's a really silly example where you have a reasonably complex structure of some different data points. And, oh look, with enough layers you can fit just about anything. But until recently, it actually proved almost impossible to train these type of deep neural networks. So what changed? So the simple answer that people often go to is just saying, well, we have better computers now, we have more data. And that certainly helps. You know, big data helped make it commercially viable. We've actually had big data for quite a long time in high-energy particle physics, and we've certainly had pretty great computing for quite a long time. There's a little bit more to it than just that. Probably the single most important was the movement towards a different type of activation function. So I mentioned the sigmoid activation function earlier. It turns out these aren't actually the best choice to make for a deep neural network. They have an interesting problem, which is that if they're saturating, then you're not going to get an interesting differential out, so you can't propagate any information through them. So you would end up with this problem where information was not reaching the beginning of the network from late in the network because you had too many saturated sigmoids. Really very, on the surface, a much more simple way of doing an activation function is ReLU, which is just a linear function and then a zero, actually turn out to do pretty great here, because you never end up with a zero gradient, which is the point at which you stop learning. That and the addition of smarter ways to train are the two things which really unlocked deep neural networks writ large. What do I mean by better ways to learn? I mean that it turns out that stochastic gradient descent is really great for finding you a better minima. Stochastic gradient descent is where instead of evaluating the entire data set, which is probably what you're used to when you train your neural networks or PBTs, instead you train a small subset. Actually, is often a practical concern. You can only evaluate in a reasonable time over a small subset. But you change that subset over time randomly or maybe progressing through your data set. And that means that instead of smoothly always taking the best possible path through your data, you take a much more jagged one. There's noise in the particular subsample of the data you look at. kicks you around this weight space. Yeah, and you actually end up with this interesting characteristic where you jump out of local minima in a way that you never would do if you were looking at the whole data set, because you added noise. So this is an unlikely but important key piece of why all this works. And in addition to those sort of like simple core things, there's continued innovation in trying to avoid the overtraining I mentioned as a concern earlier. One of the most important and really only I think empirically understood is the dropout style of regularization. Here you randomly remove whole nodes during training iterations and then you sort of upweight what's left. What that means is that because you end up with whole training phases where nodes are missing, you can't build a particularly complex set of interdependencies in the extracted features. And what you end up really training is a number of, almost like an ensemble of micro-networks through the part where you're doing your dropouts. So you end up with something which is much more robust, anecdotally at least, and in experiments, than without dropout. So people continue to push on really novel ways to regularize. And some of them, like dropout, have become default tools in most deep neural networks. The other key piece, the key piece in particular for what we're going to be looking at today, is the advent of the convolutional neural networks. So a lot of the most impressive stuff that you've seen in neural networks over the last couple of years has been powered by not a fully connected neural network like the one I showed you originally, but instead convolutional neural networks. Their secret is that they can get away with far fewer weights by understanding that their data is spatially, or in the case of natural language processing, they be temporally correlated in an interesting way. So instead, you learn weights that describe kernel operations, and you convolve those kernel operations through an input image to exaggerate useful features. You do that in layers upon layers, trained in the same way you train a regular fully connected neural network to end up getting the features that are useful for identifying a human being, or a cat, or maybe even a neutrino interaction. Here's a nice example kernel operation, a simple human-designed one for edge detection. Basically, you're going to report a central value here, and that's going to be based on the neighboring ones, but through a simple bit of linear addition. In a convolutional neural network, it would then be pushed through an activation function. But at its core, it's just learning these weights which will be applied to convolve through the image. And there are lots of pretty cartoons like this that give you a sense that go from simple things to more complex features. It's a little bit more complex than just learning one kernel operation followed by another. An actual convolutional layer will have a stack of kernel operations, which will be trained, one for each of the input layers. So even for a very simple image, it's going to be red, green, blue, say natural images. So you train one kernel operation for each of those layers of information. You convolve it through, and then you add them together to get one output. So what you end up with is M by M by H by W sort of matrix, where that's the number of incoming features, the number of outgoing features, height and width. So you actually, a given convolutional layer is going to have quite a few different kernel operations, but it's still much cheaper than training a fully connected network, because you're not taking every pixel as an input now. Instead, again, you're only learning these small kernel operations which can be involved across your images. And it's easy to see how maybe for a natural image it starts by being 3 inputs which are red, green, and blue, but for most of this network, those inputs are going to be the output of previous convolutional layers, stacks of extracted features, which will have more less useful characteristics. You can't just stack those layers forever. You need to try and think of ways to compress the information back down so you don't just run out of memory. And it turns out there are a number of ways which work very well, which are very simple for doing that. Most important is simply pooling layers. Here you just stride across an image, taking the maximum in some receptive field, and then throwing away the rest, dramatically shrinking the size of your images. So what you end up doing is becoming richer in information about what you're actually trying to identify, and poorer in spatial information as you go deeper into the network. You can bring this together to form a network which, whilst really important, already existed back in 1989, the so-called LENet, which was really good at identifying postage, and that kind of thing, actually. And here, you've got your input image. You're going to have a convolutional layer, like I showed you earlier. You're going to have some kind of pooling layer, like I showed you, maybe another convolutional layer. You could do this ad infinitum, but this network only did it a few times. And then you would sum over all your different feature maps. So each feature map becomes like a feature that you might have designed as a human being. And that goes into a fully connected network at the end to actually do the identification. Modern convolutional neural networks have somewhat more complex architectures. A lot of them feature things like this so-called network model that was existed before Google, but was particularly made popular by their inception module. Here, the real brilliance is that you're going to have the output from a previous one of these modules, which would just be a stack of feature maps. And you're going to put it through a bunch of different convolutional operations, and the kernels are different sizes. That means because the kernels are different sizes, they might be better or worse at capturing different types of features. So that's useful. But to avoid all these different combinations ending up with just a giant number of feature maps which are unwieldy, what you end up doing is using one-by-one convolutional operations to downsize feature space. Here, you're basically, that one-by-one convolution is a way to have a weighted addition of input feature maps. So that, like a fully connected layer, it gives an output, which is the sum of previous ones. I can walk through that in more detail offline if that's a little confusing, but the secret of that is being able to scale this up almost indefinitely to go as deep as you possibly want to go. And that's why they called it the inception module, a very clear call out to a particular movie. And even the first version of this in 2014, the Google Net, was some 9 layers. By now it's 28, I think was the last version of this network. Certainly this style of architecture allows you to go exceptionally deep. And it's what's powered a lot of results like the one here, where you get superhuman performance in image identification. This is actually a slightly older network, which just happens to have better graphics in it, where you can look at how the network is classifying, giving its top 5 results for a number of images it's looking at. And I think then colored in, whatever that is, beige, is the actual true label. You can see it does a pretty great job. When it gets it wrong pretty reasonably. You can do things where you look at a particular image, and then you see in the sort of training examples what images look similar, and the network's idea of similarity. I'll come back to that idea later. You can see things are reasonably grouped in these types of convolutional neural networks in a way which we kind of find naturally understandable. And the bottom line, the thing which I think caught a lot of people's interest, including my own, was just the level of performance. So the latest version, the 28-layer monstrosity I mentioned, achieved 3.46 top 5 error. That means that only 3.46% of the time did it come with an answer that wasn't where the true label wasn't in the top 5 results it gave. That's interesting because it turns out human performance of volunteers, people who are reasonably motivated, tops out at about 5%. So for image identification, we're already in the realm of somewhat superhuman performance. So how do we use all of this at NOVA? It's sort of an answer to a question of just what happens if we use these tools to try and classify our events. I love this graphic. It's from Symmetry magazine, which is based in Fermilab. It's so wonderfully melodramatic. But what do we actually do? So our input image now is a pair of maps, hits in a tight space-time window. You'll recognize that what these topologies look like from the examples I showed you earlier. Each pixel now is the calibrated energy response in one of those cells of liquid scintillator I showed you earlier. All the images have been set to have the same dimensions. It's pretty easy to center it so you capture the vast majority of the activity. And so we have about 100 planes by 80 cells. And so we have an input that already looks like it would be a great fit for this type of technology. There are some subtleties in terms of what we use for a training sample. We have quite a large set of Monte Carlo, independent from what we use for physical analysis. So we used about 5 million events, minimally pre-selected, put into non-root format, which turns out to be much faster for us, keeping 80% for training and 20% for testing. We did something a little bit interesting with those energy depositions I showed you a moment ago. Instead of just taking the raw double output, we actually rescale it to go from 0 to 255 and put them into chars. That means this data set is much smaller than it would be otherwise, which is great. It makes it much easier to ship around different processing sites. And it turns out it does a really great job of capturing the information that we actually have in these cells. There's a caveat here, which is this version of our training had a fine-tuning stage where cosmic data events were added as well. The particular way we trained here was just a timing problem. Now it trains in parallel, but not with the version that's used for this result. Our architecture is based very closely on one of the Google networks, but with far fewer reception modules. We have 3 for each view and then 1 combination. The chief architecture is that there are 2 views that go through 2 separate streams of the network. That comes from an intuition that you want to process each view separately and then combine the information later. Certainly it seemed to perform much better for us. We're trying to not just identify the type of neutrino interaction broadly by what type of charge current exchanger was. We also use it to identify the particular type of interaction, classify our chief background, which turns out to be the signal for some searches, and also cosmogenic activity, which can form a background to these little measurements.
So you have quasi-elastic RDS is elastic scattering?
Yeah, sorry. Quasi-elastic resonance, deep elastic scattering. There's actually another label, coherent, which somehow dropped off this list. The nice thing is this is put through summation, which means that you can combine these labels together to come up with a single identification. So the constraint is that the output of this network always has to sum to 1, which means that if you add together, say, all the sub-modes of nu-mu charge current interaction, you have a nu-mu charge current ID now. And it turns out that training it in parallel like this, where we don't just have signal and background, but instead we're a multi-type classifier, gives equivalent performance and allows us to run just one network that works for every analysis in the experiment, which is quite nice. Yeah, and for those who are playing with this stuff themselves, we use the Caffe framework. Keras and other Python type things are much nicer to use, but Caffe has a really good C++ API, which is great if you're going to try and deploy in an actual physics setting. So that's why we ended up using that. There was no sign of overtraining when we trained the network. Training and test loss were very close to each other. Accuracy trended up and then started to plateau. But what was it actually doing? So it's one thing to have a loss calculation and test accuracy, which look good, but you might wonder what your network is actually learning and starting to do. The nice thing with a convolutional neural network is you can actually peek inside and start to take a look. So there were a number of ways in which we tested the network, but the absolute simplest thing you can do with a convolutional neural network is actually look at the kernel operations you've learned and look at the feature maps that you're creating and see if they look reasonable. You can see that it's learned some pretty simple kernel operations at the very beginning of the network in the earliest layers. They're just pulling out blobs and lines, what we might think about as tracks or showers, when you look at the feature maps that come out the other side. And you can also peek, load. Yeah, and you can do that for different types of events and see naturally that the blobs turn up more in some of these feature maps than others already. But if we go deeper into the network and we look at, after say the first inception module, we can see the feature maps are starting to much more closely represent things that we might find physically meaningful. You can find feature maps that, for example, seem to pay a lot of attention to neon tracks, only activating for those, that for this type of interaction don't seem to do anything, but we'll see on the next slide do for others, and some which seem to care more about hadronic activity than anything else. In this example, we can see that it's not finding a neon track, which is good, because it's just an electromagnetic shower, but it's lighting up quite brightly for that electromagnetic shower with the other feature maps. And again, the same feature map seems to care a lot about the associated vertex activity, which is kind of exciting. You can try and be a little bit smarter about how you interrogate the performance of the network. So one tool which is often used with convolutional neural networks is the so-called occlusion test, where you step by step remove blocks of cells and then record what your altered PID output is at the center of the block you removed. That's going to give you a heat map, which tells you roughly about how that PID cares about the event. So here I've got 2 example events. I've got a deep inelastic scattering of an electron neutrino. It's got a nice electromagnetic shower, but it's got a lot of other activity as well that you might expect your reconstruction could get confused by. And I've got a neutral current background event, where you've got a charged pion, and it's clearly ending in a pretty heavy way, and has some associated, maybe there's a scattering going on as it travels through the detector. So this is a background to our NUMU charged current result. And now if I do this occlusion test and I record on the left-hand side the NUI PID output and how that's changing, and on the right-hand side the NC, the NUMU charged current output, see how that changes. Two interesting things come out. First of all, you see that the electroneutrino ID really only seems to care about the actual electromagnetic shower. And if you start to mess with that, it starts to dramatically reduce how NUI-like it thinks the interaction is. So it's paying attention to the part you'd hope it would be using to do identification with, and it's not really misled by any of the other heavy hydraulic activity in this interaction. And for the case of this background event, it starts off correctly identified as a background event, but we can make it think that it's a signal event when we delete the hits which it's using to work out it's a pion. If you remove the hits associated with the scatter or where it's ended the track, it starts to think it looks like a muon instead. It dramatically increases the score for it being a muon charge current interaction. These are all semi-anecdotal ways of studying the performance of the network, but it's still really nice to see that it seems to be paying attention to the same things that you might do as a hand scanner looking through the events.
So I have a question. This might be a well-thought-out question. But where's energy on this axis? So this is like, these are kind of just like tracks.
Not on this. No,
so I mean, is that used at all in this?
So an interesting question is how sensitive you are to energy response of this. Because of the way you downsize spatially, you're not going to end up with a really complex DDX profile. It's going to be more topological than that. You might think about trying to combine that information with this, or with playing with not downsizing as aggressively as we do in this current network to preserve information. So there's room to maybe do a little bit better there. But right now, it doesn't use too much energy information.
So you're just tracks that you see?
So it does.
And like the different colors, like your different colors.
Yeah, so there is, on this Colsey plot, the Z-scale is energy, and it's there we go. MEVs, basically, and it's in the steps here, so it's kind of a low-res energy response per cell. So there is energy information there, it's just not the most important part that's used by the convolutional neural network. It's more sensitive to on or off rather than the magnitude of the energy response. That's not 100% true, and I think that's part of why it's paying attention to the end of that muon track in the way that it does. Anyway, as I said, this is sort of an anecdotal way to probe the behavior of a network, but these was a nice ways to check that it's doing roughly what you'd expect it to do. There are also slightly more complex ways to examine the performance of the network, particularly the t-SNE, stochastic neighbor embedding way of looking at the associations in your network. So here, I've taken the final features of the network just before it goes into a fully connected layer to do the actual identification. And I use that to come up with just a 2D map, a projection of how closely related different examples are from the test sample. The labels are from truth, yeah, it's just a small subsample of the events. And I've shown also example pixel maps of what the events look like, so you get a sense as a human being of how these groupings work. It breaks down along a couple of really interesting axes. You end up with your NUMU events very separate from your NUI events, which makes sense. A muon is unlikely to look too much like an electromagnetic shower. They do connect a little bit, but that's in the cases where all the energy has gone into the hydraulic component in a pinor. Neutral currents live between them. As you saw earlier, the challenging background that can be a background for either of these samples. And you can see an axis related to quasi-elastic versus deep elastic scattering, how much energy ended up in the lepton versus the hydraulic component, and it breaks down pretty nicely. And what I like about this is you can see the axis is the same across this way, so there's some understanding in the network that what it's using to classify as DIS is the same across these two samples. These are more similar than these are similar to each other, which is really kind of interesting. So maybe you've convinced yourself that it's not doing anything too crazy, and test accuracy looks great, but what is the bottom line performance like? Well, if we actually now plot realistic set of distributions where you apply oscillations, some of our more regular rejection cuts and data quality cuts. You end up with these really nice PID distributions for the NUMU classifier on the left and the NUMU one on the right. Straight away, you can see that you're getting pretty good separation from your backgrounds. On the left-hand side, you can see the NUMU one is doing very well. It's actually doesn't do much better than the KNN selector, which tells you that muons are hard to miss. That statement, sadly I don't have anything blessed to show you today by my collaboration, but it turns out that when you go down to lower NGs, you can save some events with CBN that is classified that you wouldn't be able to do with the KNN. So there is actually a reason to use it there, where oscillation information is richest. And that was correlated to doing better at cosmic projection. But the real star of the show is the electron neutrino performance, where we get some 73% efficiency, 76% purity. If you go for a signal over square signal backward optimized cut, the killer here is that compared to either of our previous very well developed conventional, more conventional PIDs, this was equivalent to 30% more exposure to get the same font, which is pretty great. So you can tell that you want to use this. And yeah, I should say that the the remaining backgrounds, two things. The largest is neutral current interactions, but they're ones which have a pi naught of some reasonable energy, so that kind of makes sense. And the runner-up, the intrinsic contamination of our muon neutrino beam, turns out there's a very small fraction of electron neutrinos which we correctly would call signal because they're identical to our signal sample. And some very rare other interactions which have got energetic pi naughts and the order cosmic event. Okay, so what did we have to do to actually take this from looks great in Monte Carlo to using it in actual analysis? So first of all, we're a two-detector experiment, so we can look at our near detector and see what things look like. We look at our signal, which of appearance of the far detector. Thankfully, we saw that the PID gave exceptional performance across the full classifier range of our data sample. And if we zoom in the region that we'd like to cut in, the agreement continues to be excellent, particularly within our uncertainties. It's true that that selected sample also had pretty great kinematic agreement. There's no cause for alarm from that perspective. But that really only tells you about your near detector and only tells you about your background events, which are clearly going to be somewhat distinct from your signal. But we have a way to fake our signal sample of the near detector with a hybrid data Monte Carlo fusion sample. So here, this is the so-called muon-removed electron added sample. We use our simple KNN to find a muon-neutrino charge current interaction and to identify a track that we might call a muon. We remove those hits and reconstruct the energy of the muon we think we removed, and we replace it with a simulated electromagnetic shower of the same energy. So what this does is it gets you topologies that aren't reliant on your generator for neutrino interaction cross-sections. They come direct from nature and what you've recorded in your detector. And you only replace the thing that you're probably doing the best job of simulating, which is your electromagnetic shower. When we do that and we look at performance, we see exceptional agreement between data and Monte Carlo in that MRA sample. And actually, the thing that I particularly enjoyed about this was that the performance was closer in the deep learning network than it was in the conventional networks, suggesting perhaps they were a little bit more overtrained than we were. You can also, if you're worried about our far detector simulation being wrong somehow, maybe you worry about us getting the response as a function of cell length right or something like that. We actually have a special sample of cosmics we can play with, taking cosmic muons with a Bremsstrahlung shower, pulling off the muon, just looking at the electromagnetic shower, and looking at that in data Monte Carlo. The story is the same as with MRE. The performance of CBN or those electromagnetic showers is pretty much identical between our cosmic data and Monte Carlo, which is great. In terms of actually using in the analysis, systematics were explored in a very robust way, which is actually creating a whole systematically shifted data sets and looking at how your analysis changes. An interesting thing you get out of that is that calibration response, the energy response, does turn out to be one of the more important ones, but really more for the background of the signal. And cross-section assumptions also turn out to be really important. Normalization for signal uncertainty isn't really anything to do with PID, and all the others turn out to be useful. So we end up with a final error, which is not tiny, but well understood, 5% of the signal, 10% of the background, certainly much smaller than the statistical SMTs. So after doing these cross-checks, we decided to use it for our appearance analysis and opened the box and looked at some lovely data. We saw 33 events, which agreed very well with our prediction from our best fit. And the far detector continued, just like in the near detector, to have really excellent data Monte Carlo improvement in kinematic variables and things like that, which was great to see. And I should say, I should put a citation here. This is now a published result. I didn't put the contour here because I didn't want to make it this electron appearance talk. But yeah, it was a delight to see it actually used and deployed. Moving forward, the original dream was to go beyond reconstruction. The reality is a little bit more complicated. It's very likely that we're going to continue to use deep learning in combination with conventional reconstruction tools. Perhaps as an input to them. So one of the most exciting options out there right now for neutrino physics, where we've got these really nice spatially uniform detectors, is that it would be a great place to use a type of convolutional neural network called a semantic segmentation network. Or there are some varieties as well. But basically, you want to identify individual pixels in your event display. That then could be used as the input to your event reconstruction. So instead of just having space and time information, you can have for every hit in your detector also a confidence of being a muon, which would allow you to better pull out muon tracks and noisy environments and stuff like that. People continue to play with recurrent neural networks. You, of course, have seen this in the world of collider physics for really cool jet tasks. We could use it for signal processing, maybe for NG estimation, hopping through reconstructed tracks and showers instead of through different reconstructed jets. It really is a natural fit for some pattern recognition tasks. And probably most exciting in general for particle physics right now is work towards adversarial networks. Adding lots of nuance to your training operation instead of having just a really simple loss calculation. By pitting your regular network against an adversarial network, which presses opposite optimization in a opposed direction. It's a really nice example as well of how deep learning and science can come together, and it's nice to see that science is high into particle physics science. My favorite example of this comes from Carl Kramer and Charles Lupe at NYU, learning to pivot with adversarial networks, and I thought it was really exciting to see Jan LeCun, the guy who invented convolutional neural networks, tweeting excitedly about a talk from Carl at one of the big machine learning conferences last year. And I should say that obviously a lot of different experiments are looking at this right now, so I'll just run through these quickly. Diabase does some really cool stuff with data. Microbrune are doing very similar things to Nova, just a couple of months behind. Minerva are really interested in trying to use it to work out exactly what nuclear target their neutrino interactions struck in their very complicated detector. Lariat and Proto-June building towards the June experiment. We'll try and use this to make the most out of their very complex liquid argon TPC data. Atlas, of course, has looked at convolutional networks, though I think it's having most success now with recurrent neural networks for jet physics. And our astrophysics colleagues are also beginning to use these tools for things like gravitational lensing, which is really exciting to see as well. Okay, yeah, so just to conclude, our Nova electron neutrino appearance result was the first that I'm aware of, certainly, to use deep learning for an actual physics measurement. It's actually also already used in our first sterile neutrino analysis, which was published just a couple of months ago, and is being explored as an option for a number of other searches. In fact, in the updated muon neutrino disappearance search coming out in a week or two, it's going to be a core component of that as well. And I should say this is just the tip of the iceberg. There's a huge amount that we can continue to do, that our field can continue to do with these tools. If you want to, you can read our paper describing the network that I talked to you about today. And if you're interested in plugging into a wider community of people using these tools, there's a really exciting group based at Fermilab that are active on Slack if you have any questions. So thank you very much.
That's a good talk. Are there any questions?
Think about other experiments. So the idea is like discriminate between mu and electron. It's like ice cube. Is this like some?
Yeah, I sort of wondered about that. I think the nice thing is they have loads of GPUs already as well, because they use it for their light simulation. But I haven't heard of anyone trying it yet.
Okay.
It's hard to believe it's not being attempted. One place that it's being used is the direct competitor to Nova, which is SuperK is looking at the possibility.
Actually, I was going to ask about SuperK.
Yeah.
Okay.
They're only just starting to play with it right now, but I know that a close colleague of mine that also works in this kind of work does some great stuff. I just realized that I should have highlighted Adam Orsano during this talk. I'm now wondering if I can point to a picture of him in this collaboration photo. So one of the people I've worked with most closely on this work is Adam Orsano. Where is he? Who of course went here for grad school. He's actually, you'll see that he's a co-author on this paper with me. But yeah, people are just starting to look at this now for the other neutrino experiments. It's particularly popular on liquid argon experiments because conventional reconstruction is having a really hard time with the richness of the data they have. It's actually an interesting culture problem there because ideally you would come up with this tool after you already had robust existing reconstruction so you can validate and you can do things like the data-driven cross-checks that I showed you without needing deep learning to do those cross-checks. But they don't really have those tools, so how they work out how to navigate that in that case would be really interesting.
So like the cross sections for something like Minerva, like the nuclear cross sections tend to be there's lots of uncertainty that comes in here. I mean, is it bad for something like Nova or?
Cross section uncertainties are really important. So actually, one of the cool things was that muon removed electron added sample that I showed you. The special hybrid data set. It has really great agreement now. It didn't have great agreement until we added the so-called 2p2h channel, which is recently like a big thing in cross-section theory, which is a special intranuclear interaction that perturbs your cross-section for things which look an awful lot like quasi-elastic interactions. That affects the efficiency of your PIDs because quasi-elastics is so much easier to identify than anything else. And it meant that our data sample of MRE and our Monte Carlo sample of MRE actually disagreed by a few percent. Once we added in even a simple version of that, it got much better.
So the examples that you mentioned of experiments that have used deep learning, I don't think, none of them were direct detection experiments, right?
Might be true.
Is that just a cultural thing, or?
Like the dark matter experiments, direct dark matter?
Sorry?
Yeah. Direct dark matter detection?
Yeah.
I guess they're like, is there readouts is complicated? I'm not sure.
Yeah. I think the next experiment is looking at deep learning. I think there's Xenon, right? So they have some, yes, I think.
Is that a double beta decay, or is that I always get confused which ones?
Yeah, that's double.
They're kind of like they're kind of morphing together at the stage.
Oh, really?
The double beta decay and the dark matter.
Those low background searches. So in situations where you have like a liquid xenon detector, then maybe it can make sense because again, there's some pretty rich information there. But for others, where it's not quite the right type of data or anything. And there is also a cultural problem, which is if you're trying to convince people that you've discovered something, it might be a little bit harder than to convince people you made a good parameter measurement with a ratio.
Yes. Okay. Because they're more likely to see a null measurement than a measurement.
Yeah.
Okay.
It's a really interesting cultural question, and I don't have a good answer.
Okay.
But, and I think that people are going to almost everywhere be looking at these tools in some way or another, and partly because it's exciting for graduate students. They're going to want to play with it.
Yes. Yeah. Are there any other questions? Okay. Let's guys want to come to topic chat? Sorry.
I have to do something. Half an hour. Half an hour.
Yeah, we can talk a little bit.
Okay. Okay. All right. Well, thanks for hearing it.